Hello everyone, welcome to GATE Academy Global. Today we are going to start another new portion of first unit, that is basic semiconductor physics, and that portion is very important for GATE point of view, and that portion is nothing but low level injection. So we are going to see low level injection. So I have a question for you, that do you have high level injection also, or we don't have anything that resembles high level injection? Okay. So think about these particular questions. Those who are attending the classes, Sharika, Abdul Lakshmi, Amit Narendra, and Shri Krishna, Pooja, Veena and Chandra. Okay. So think about this one, that if you have low level injection, then there is something that resembles high level injection or not, and in which device we are using this high level injection concepts, and in which device we are using low level injection concept. Okay, so before starting this low level injection in our particular series or crash course sequence, we are going to understand the process of diffusion inside a semiconductor. Then only we can understand what is actually low level injection. So I am going to start the process of diffusion, and there afterwards I am going to deal with this low level injection. So today is the conceptual making day, and tomorrow we are going to deal with some question that is based on this low level injection and diffusion current. So we have so many confusion on diffusions also, and we are going to deal with diffusion slowly, and then we are going to deal with low level injection. Okay. So I am going to start from the concept of diffusion. So concept of diffusion in semiconductor. This is today's agenda. Then we are going to deal with the particular point, that is low level injection. So what is the concept of diffusion? So concept of diffusion starts from another word terminology that is known as for non-uniform doping. Uniform doping, we are having the concept of diffusion inside a semiconductor. Okay. So what is non-uniform doping? If the doping concentration in a semiconductor is different at different positions or with respect to distance, if the concentration is changing, if with respect to distance, if the concentration is changing, then we can say that there exists a movement of charge carriers from higher concentration to lower concentration. Whenever there exists a movement of charge carriers from higher concentration to lower concentration, definitely there exists a concept of diffusion current. Okay. So suppose this is a semiconductor, and in this semiconductor we mark two different points. Okay. So just I want to draw this one in a graphical plot. So I will have taken an x-axis, and on the other side we are going to take an y-axis. So I will just take this x-axis as the distance. So this is the distance x in centimeter, and we are going to take the y-axis in this particular way. So now what will happen at two different points? Okay, suppose I am taking, this is x1 distance. Okay, I have taken, this is the distance, suppose x1, and this is the similar one, we are taking x2. These are the two different points, and we have to dope this semiconductor non-uniformly, non-uniform doping. So initially the semiconductor is made up of silicon, and while adding the extrinsic material, that is the impurities to this semiconductor, which is nothing but the donor atoms or acceptor atoms, we are going to see that whether the diffusion is uniform inside the semiconductor or non-uniform inside the semiconductor. So suppose the diffusion is non-uniform, then I would like to say that we are having the doping is non-uniform, that is we are having ND1 here and ND2 here. So initially what we are doing for a uniform doping, if I say this word that the semiconductor is overall uniform doping, for uniform doping, what I can say that ND1 is equal to ND2. Okay. So this is the for uniform doping concentration. And secondly, for if I use the another terminology, that is for non-uniform doping concentration, that is for non-uniform doping concentration. So I would like to say that non-uniform doping, then I can say that the ND1 is not equal to ND2. So, ND1 is not equal to ND2. So, this is called non-uniform doping. So, suppose this semiconductor is non-uniform doping, then what will happen? Hello sir, I am from Maharashtra. Your lecture is very helpful for me. Thank you so much. Thank you Shri Krishna. I have seen that you are attending my classes every time, and very happy to see you in the morning. Okay. And Prithvi Srinivas, happy morning sir. Yes, happy morning. Okay. So, just I am taking this is ND1 and ND2, and non-uniform doping means ND1 is not equal to ND2. Suppose in the similar principle I would like to take ND1 is greater than ND2, then what will happen? The concentration of donor atoms at one side will be greater than the concentration of donor atom on the other side. So, we know that at 300 Kelvin all donor atoms are ionized. Okay. So, if I place this semiconductor at 300 Kelvin, then I can write here at 300 Kelvin, learn each and every point slowly. Okay. At 300 Kelvin what will happen? At 300 Kelvin the donor atoms are 100% ionized. So, donor atoms are 100% ionized. So, donor atoms are ionized, and what is the ionization rate? It is 100% ionized. If the donor atoms are 100% ionized, each and every donor atoms inside this semiconductor will donate one of the electrons to the semiconductor itself. So, we are having so many electrons and so many electrons here also, but the concentration of electrons at this side will be greater than the concentration of electrons on the other side. If I am taking that, suppose here we are having N1 is the concentration of electrons on this side and N2 is the concentration of electrons on the other side at distance x2, then we can write then N1 is greater than N2. This is known as non-uniform doping. So, at this particular point what will happen? Sir, the electrons concentration from the higher side tries to move to the lower side, so that the concentration of electrons on both sides of the semiconductor with respect to its distance will be equalized. This is the natural principle of every matters, either it is solid, liquid or gaseous material. A solid which is known as the microscopic particles, they will move from higher concentration to lower concentration whenever there is a concentration difference, and we have seen the water body, that means the water reservoir. Suppose at one side we are having the concentration of water will be very much, or the content of water will be very much, then the other side that definitely the water will flow from a higher concentration to lower concentration, or higher water content body or reservoir to lower content. Okay. Similarly, in gaseous material we will have the smoke. Suppose we burn something and we close this particular box or smoke within a box, then what will happen? The smoke is coming out. The reason the smoke is coming out is because of the concentration difference. So, whenever there is a concentration difference, always the microscopic particles in solid and in liquid and in gaseous material, they move from the higher region to lower region. So, this is why we are having the charge carriers are also moving. So, I can say that now we are going to draw another way, that I can say suppose we are having electrons, so many electrons on one side higher, and here we are, as we are moving along the distance, the concentration of electrons are decreasing, and this is known as non-uniform doping. This is known as non-uniform doping. Now, what will happen? The electrons from the highly concentrated side will move to the lower concentration side. This is the movement of electrons. So, I just write here, this is the electron which is moving from highly concentrated side to lower concentrated side. This is the direction of movement of electrons. So, if the electrons are moving, then definitely what will happen? Suppose at this side we are having some of the atoms, because the initially what we have doped with donor atoms. So, donor atoms consist of what, or how we can resemble a donor atoms? If you think about donor atoms, the donor atoms is a neutralized atom, and whenever one of the electrons leave the atom and move to the semiconductor, then what will happen? The donor atom will get ionized. What is the charge gained by the donor atoms when it will become ionized? The charge is nothing but the positive charge, because it has donated one of its electrons. I think you are listening me properly, then only you are going to get, because I am saying so many things together in a small change in time. So, that is why we have to listen carefully. Okay. So, what will happen? Sir, if the electrons is moving in from this side, then definitely we are having some of the ions that is present on the other side, and these ions are definitely having the positive charge. So, here we are having positively charged ions, and since the electrons has gone to the other side, definitely we are having a negatively charged electrons on the other side. So, what will happen? The positive on this side and negative on the other side. What will happen? There must be a because of the concentration difference, there must be a potential difference also, but we are going to look at this potential difference later. Now, we have to think about the electrons that is moving from the left hand side to right hand side because of the concentration difference. So, whenever the electrons are moving from one side to another side because of the concentration difference, definitely we know the movement of electrons will give a current. Okay. So, rate of flow of charge is nothing but the current. So, we have a current. What will be the direction of current? Always we are taking the conventional direction of current is always opposite to the direction of movement of electrons. So, definitely we are having a current in the opposite direction. What is the direction of current? If the electrons is moving in a positive x direction, definitely we are having the current in the negative x direction. So, we are having a current, and this current is obviously called diffusion current. So, I just write here, this is known as I diffusion. So, this is known as I diffusion. So, how to find out this I diffusion? This is the main question. So, for finding out this I diffusion, we just have to take the formula that is known as, either we can say the diffusion current density or diffusion current. So, there are two things that we are going to consider here. The first one is, we are taking, this is known as diffusion current density, So, we have seen the current is existing, and this is known as diffusion current density. So, we just write here, this is known as diffusion current density. So, what is diffusion current density? If the charge carriers are moving because of concentration difference within the semiconductor itself, then the current that has been generated due to the movement of charge carriers, which is because of the concentration gradient, is known as diffusion current density. So, diffusion current density due to electrons is represented by Jn. This is J with subscript n, and this is directly proportional to the concentration gradient. What is concentration gradient? Gradient always resembles the change with respect to distance. Gradient always resembles the change with respect to distance. So, here we are having dN by dx. What is this n represents? N represents the concentration of electrons, and dN or dou n representing the small change in the concentration with respect to a small change in distance. So, we have to know this one. Whenever this small change in concentration with respect to a small change in distance exists inside a semiconductor, then we can say there exists another thing which is known as the diffusion current density. So, to finding out the proportionality constant here, we just write here, this diffusion current density can be represented by Jn, and the proportionality constant here is nothing but diffusion constant, and since this is nothing but the number of electrons per unit volume. So, we have to make this one charge. So, to make this one charge, we have to multiply with charge q, and then we can write here again dN by dx. So, this is the equation which is representing the diffusion current density due to electrons. So, when this diffusion current density exists, so this diffusion current density exists whenever there is a concentration difference within a small distance within the semiconductor itself. So, here we are writing the unit of this one, the unit is ampere per centimeter square, because this is a current density. So, always it is resemble with respect to centimeter square. Okay. Option teaching, sir, please make also video in on numericals on each topics if possible, sir. Yesterday, if you haven't seen Ramesh, then we have discussed about the numerical problems of the previous, that is the Fermi energy level. So, just watch the previous lecture, just what I have taken in yesterday's class on 29th October, you can see that we have discussed. So, numerical problems always discussed if we have completed this one, that is nothing but the conceptual part of any particular topic. Okay, Omkar Sutar, welcome, love you from Maharashtra. Okay, thank you. Okay, so I have seen that you have come to know about diffusion current density. We can make this one as diffusion current also. So, what is current? Sir, current is always written by, current is nothing but the rate of flow of charge, and if you know what is current density, the current density is nothing but current per unit area. So, I just write here, this is the current density and this is nothing but the current per unit area. So, if you want to write what is current here, then we just take this one, this is I n is equal to, this is A q dn and this is dn by dx. This is the way by which we can put this equation. So, there is a small confusion between the signs, what is the sign that we have to take here. So, I am going to reduce that confusion by using this particular lecture. So, here see once, here we have taken the electrons as the charge carriers and these electrons are moving because of this concentration difference. Suppose similarly we are having some concentration difference of holes, then what will happen? Suppose in the similar semiconductor, if we have the concentration difference of holes, then we can analyze this one in the similar way, but we have to check the sign. So, what is the sign? So, first of all we are taking one by one the sign. What is the confusion here? Because this is the crash course. I have to clear all your doubts that we have while solving the questions. Okay. So, this is dn by dx. So, just I am taking dn by dx. I want to say, suppose the concentration is changing linearly with respect to distance. I am supposing a thing that is suppose the concentration within the semiconductor is changing or varying, changing linearly, I just write here linearly with respect to distance. So, this is with respect to distance. Then what we can say, that if it is changing linearly, then we can write this dn by dx, this dn by dx can be written as, this is n1 minus n2 divided by, we can write this is x1 minus x2. This is the linear change, and if it is changing linearly, we can write in this order. Now, from the previous figure, we just find out what is n1 and n2. Since I said that n1 is greater than n2, but if you take the distance which is changing with respect to distance, then x1 should be less than x2. So, n1 should be greater than n2, but x1 should be less than x2. So, I just write here, this is x1 should be less than x2. So, if you write the concentration gradient means change in concentration with respect to distance, that is represented by n1 minus n2 divided by the corresponding distance, that is x1 minus x2 we have to write. Then we know that n1 is greater than n2, then we are having a positive value here. Then if x1 is greater than x2, then we are having a x2 is greater than x1, then we are having a negative value. Overall, this will become a negative one. So, if this is a negative magnitude, this is having a negative magnitude. What is having a magnitude? The concentration gradient is having a negative magnitude. So, if you write the concentration gradient in this particular equation in a negative way, then we can write this will give a negative value. So, if this is giving a negative value, then we can have the current density which consists of this particular expression which is having a negative value. Then overall this current density is also having a negative value. See, since the current density is having a negative value, what it resembles? It resembles that the direction of current is in the negative x direction. So, if you watch this particular figure and if you see the direction of current that I have drawn here is in the negative x direction. So, negative magnitude of current resembles in the diffusion current. So, I just write here the final thing. What is the final thing? The negative magnitude of current. So, I just write here the negative magnitude of current in a I just write in this way, negative value, not magnitude. So, negative value of current in diffusion is representing the direction of current is in negative x. So, this is very important thing because most of the students will have some confusion about this one. So, here in this diffusion current we are having so many confusion. Today morning also some of the student asked me about the confusion that they are facing while solving the question of diffusion current. So, I just clear one by one what are the confusion do you have, why don't we and I or faculty don't have any confusion, why you are only having confusion. The reason is that we have not found the exact theory behind this diffusion current. So, now we have said that whenever we are having the current in the negative x direction and the charge carriers, that is the electrons, are moving in the positive x direction, then only we are having the negative x direction current. Then what we can say, the current is having a negative magnitude. The reason of current is having a negative magnitude because the current is flowing in the negative x direction. So, in this equation we do not have to put any negative sign explicitly in this particular equation. We do not have to put any negative sign because if you open this dn by dx, then definitely we are having a negative sign. So, we do not have to resemble any negative sign extra or added negative sign in this particular expression, so that we can get a negative current or negative current density. So, very easy to understand. Now, what is dn? dn is nothing but how easily the charge carriers are moving within a semiconductor whenever we are having the concentration difference. This is known as diffusion coefficient, diffusivity or diffusion constant. So, I just write here this dn is known as, this is known as diffusivity, or it is also called diffusion constant or diffusion coefficient. So, this current is similar to the mobility, diffusivity and mobility. So, how we can connect this word with mobility? So, can you tell me what is mobility, mu n? So, mu n resembles the mobility. So, what is mobility? If you understand these things, mobility is nothing but the movement of charge carriers, how easily, or we can say how fast the charge carriers are moving in a semiconductor due to presence of electric field. So, whenever electric field are present, then definitely we are having the mobility is the principle, and similarly we are having diffusivity. So, what is diffusivity or diffusion constant or diffusion coefficient? It resembles how easily or how fast the charge carriers are moving in a semiconductor due to presence of concentration difference. So, whenever we are having concentration difference, then the reason or how fastly the charge carriers are moving, that is representing by the diffusivity. And if we are having the electric field, the overall theory behind this one is nothing but the electric field here, and here we are having concentration difference. So, whenever we are having concentration difference within a semiconductor, then how fastly the charge carriers are moving inside the semiconductor due to the presence of concentration difference will represent the diffusivity. We do not have to find out mobility and diffusivity by ourselves, because this particular value has been found out by doing some practical work. So, whenever in gate problems we have the questions based on this diffusion current or diffusivity, they always provide me the value of diffusivity, or if not, then they will provide the extra particular parameters which will be used to find out the problems of the diffusivity or the value of the diffusivity. So, do not think that we have to by heart the values of this diffusivity, this is not required. Okay. So, another way by which we can connect this diffusivity and this mobility is nothing but the Einstein relationship. What is this Einstein relationship? We know that we are having a relationship that resembles, thanks to all GATE Academy team sir, and a huge respect deep from heart. Thank you Abdul Khalik Khan. Okay. And Mubarak for your festival or our festival from all over India, we are celebrating this one. Okay. So, we are having the relationship, and that relationship is nothing but the relationship between Dn and mu n. We can derive this one also, and we can find out that I have some of the videos in which I have derived this equation also. It is present in YouTube channel of GATE Academy. So, dn by mu n is equal to dp by mu p, then again we are having one value that is known as Vt. This is known as Einstein relationship, and by using this one we can find out the value of d1 and dn by dp, and this dn can be find out by using the relationship. Suppose anyone want to find out the value of dn at any particular temperature, then we have to multiply the mobility in that temperature with the energy, or we can say volt equivalent of temperature, that is Vt. So, this one is the formula by which can connect this dn with mobility and the energy, or we can say the voltage. This is known as volt equivalent of temperature Vt. So, I think I have given so many things right now here. So, understand the concept behind this diffusion constant and diffusivity, and in addition to that we have connected the similar one with the signs also. So, the sign means the negative and positive sign. So, suppose if anyone from this class may have, if they have the understanding behind this one, then they have the question that suppose sir, we are having this following figure can be drawn in this way, and this line representing the concentration with respect to per centimeter cube, and we are having this line representing the distance in a case of centimeter. Then suppose the electrons concentration on this side N2 and the electrons concentration on this side N1, N1 representing this particular point and N2 representing this particular point, and we are having x1 here and this is x2. Then if someone asked me to find out the equation or the signs in which the current is present inside this semiconductor body, then if this is changing linearly with respect to distance, suppose this is changing linearly with respect to distance, what is changing? Concentration is changing within the semiconductor with respect to distance. Then the electron is moving in this direction. So, electron is moving in the negative x direction. This is the direction of movement of electrons, because the concentration of electrons at distance x2 is greater than the concentration of electrons at distance x1. Then the direction of current in this particular figure will be in this direction. So, if the direction of current is in this direction, then we are having the positive x direction of current, and this is given by In, or we can write In diffusion also, because we are concerning about the diffusion current. Then Sir, equation IN diffusion, then in this particular context, do we have to put a negative sign? Then because the current is in the positive x direction, so we are having dN by dx always negative. They may think about this one, and this is the equation dN by dx. Would have to put in this order? No, again we have to put a positive sign. The reason is that based on this one, this equation, okay, we are having what is the value? DN by dx. So here we are having q dN, and suppose the change is linear, then we are having this is n2 minus n1 suppose divided by x2 minus x1. Okay, the similar thing that we have to put here, and we are finding the IN diffusion here. Then if you see that the current is in the positive x direction, then the result of this one, since n2 is greater than n1, observe here n2 is greater than n1, because n2 resembles this particular point which is greater in concentration, n1 represent this particular point. So this is n2 and this is n1. So n2 is greater than n1, similarly x2 is greater than x1. So overall this particular value will give a positive sign. So this will give, what will have give? Sir, this will give a positive sign. So overall this current I diffusion will give a positive sign. So I can write here the IN diffusion here with its value, then its value is a positive value. So its value is a positive. What does it represent? This positive value of diffusion current. Okay. So I have to multiply cross sectional area A also, otherwise you have a great confusion here. Okay, because I have discussing about the diffusion current, not diffusion current density. So this positive sign resembles what? The direction of current is in positive x direction. So direction of conventional current, direction of current is positive x direction. Current is positive x direction. So no need to think about anything else. Can you learn in all formula? In EDC it is a sufficient for? No, Akshat Jain, if you only learn the formula, that is not sufficient. We have to think about those formula, how it came, what are the parameters, what are the steps. Yesterday also I said the same thing. If you have not attended the class, then attend each and every class. You are going to get each and every answer that you want to ask me about this EDC subject, because I know each and every doubts that we have because of my experience. That's why I am telling you that attend each and every classes. Then we have a proper concept, proper revision, proper formulas, steps, constant, what this constant is representing, each and every points you are getting. Okay, only by heading the formula will not clear the subject of EDC, and you are not going to get any marks. Okay. Okay, so see, your comment box consists of, are you a GATE aspirants? If yes, then fill this form. So please fill these forms. We are going to give you some more concepts behind, or this particular GATE 21. We are going to provide some more things. That's why we are going to connect. We are collecting the data from you, that how many of the students are interested in GATE 21. So by collecting those data, we are going to provide some more theories, some more practice problems based on this. Okay. So please fill the form. You can see the link is there. Okay. This is a Google form. Please fill the form. Okay. Next, we are going to take another thing, that is nothing but the direction of current is positive x direction. So if you are talking about an n-type semiconductor, then whether we are having whatever n-type semiconductor, okay, and if this n-type semiconductor is non-uniformly doped semiconductor, non-uniformly doped semiconductor, then what will happen? We are having diffusion current. So if n-type semiconductor are non-uniform, then we are having some diffusion current within the semiconductor, and we have to just use this equation without any sign. What is the equation? If you are taking about Jn and this is Jn diffusion. Just I am writing the full thing because we are having another current that is known as drift current. So, Jn diffusion is given by q dn and dn by dx without putting any sign extra in this particular equation. So, this is having the unit that is ampere per centimeter square because this is diffusion current density, and we are having another equation that is In diffusion, and this is having the similar one that is q dn and dn by dx, and this is multiplied by n. Unit is ampere. What is the unit? This is the cross sectional area and unit is ampere. So, these are the two things. Okay. Similarly, Najia Ranesh, okay, thanks Gate Academy. Thank you Najia. You are following my lectures. I can see that you are attending each and every lectures of mine, and you are going to get a good concept. So, suppose in the similar way we are talking about, this is N type semiconductor, now we are talking about a P type semiconductor, and this is again a non-uniformly doped semiconductor, So, if it is again a non-uniformly doped semiconductor, that means the concentration is changing with respect to distance, then we are having again diffusion current within the semiconductor. So, diffusion current, this diffusion current is always present within the semiconductor. The area or the distance in which we are having the concentration difference, that is why this part is very important here. What is the part? This part is very important. So, diffusion current are again existing within the semiconductor. Diffusion current exist, okay, but the important thing is there, this is always existing within the semiconductor in which we are having the non-uniform doping. This will not go out of the semiconductor. So, there is no diffusion current out of the semiconductor. I am going to tell you that why I am talking about out of the semiconductor also. And the equation that is resembling this one, what are the equation? That is Jp, okay, and diffusion. Jp diffusion if you are talking about, then we just write here this is minus q and dp, then we are having dp by dx. We have to put an extra negative sign at this particular equation of diffusion current in which we are considering holes which is changing with respect to distance. So, this is dp by dx, that means the holes which is changing with respect to distance. And what is the unit of this one? The unit of this one is ampere per centimeter square because this is diffusion current density. So, in addition to this we are taking another one that is nothing but Jp, okay, Ip, okay, current density, then we are having current, okay, Ip diffusion. So, what is Ip diffusion? This is minus q and dp, and we are having dp by dx and multiplied by a, and the unit is what? Sir, unit is ampere here. So, here we have to take care of the unit, and the unit is ampere. So, why we are putting a negative sign here? The reason of putting this negative sign will be explained in the next slide. Okay, I am taking a next slide, and I just want to maintain a concentration difference by using a holes, by using some of the holes. So, we are having a p type semiconductor. How we can construct a p type semiconductor with non-uniform doping? So, suppose this is a semiconductor and it is a p type semiconductor with non-uniform doping. So, here we have drawn each and every point because I haven't given an idea about the cross section. Cross section is always taking in the direction perpendicular to the direction of movement of charge carriers or direction of current. So, this is the cross sectional area. Which one is cross sectional area? Sir, this is the cross sectional area, and in current we are taking this cross sectional area. So, this area is always taken in the direction which is perpendicular to the direction of movement of charge carriers or which is perpendicular to direction of current, okay, this cross sectional area. So, here we are taking one by one. Suppose we have doped this semiconductor non-uniformly, suppose this is Na and on the other side we are having Na, but here we are having Na1 and Na2, and I want to say that Na1 is not equal to Na2. That means the concentration of Na1 will be greater than the concentration of Na2. Then we know that at 300 Kelvin each of every atoms within the semiconductor will get ionized. So, how this one will get ionized? Ionized means it will accept one of the electrons. So, in this way we can say that whenever there must be a ionization, there must be existence of holes within the semiconductor if it is a p-type semiconductor. So, I can say that we are having the holes concentration which is changing with respect to distance. So, suppose we are going to take a graphical plot, again we have taken the two distance, and in this two distance we are having the concentration of holes here P1 and concentration of holes here P2, and this one has been maintained due to the movement of charge carriers. And if P1 is greater than P2, then definitely there must be a concentration gradient. So, dP by dx, if it is linearly changing with respect to distance, linearly changing, then we can directly write that dP by dx can also be written as this is P1 minus P2 divided by, we can write this one as x1 minus x2. So, this is P1 minus P2 divided by, we just write this one as x1 minus x2. Okay, this is the way. So, now we are having P1 minus P2 is what? Sir, P1 minus P2 is nothing but the concentration difference. If P1 is greater than P2, we just have a value which is positive, and x1 minus x2 is again the change in distance, and this will give a negative value. Okay, this will give a negative value because x2 is greater than x1. So, whenever we are having the holes concentration which is changing with respect to distance, then definitely we are having this particular way of expression, and overall this will give a negative sign again. Google form is not accepting my contact number. Okay, take care Ankush. Okay. So, we are having a negative sign P1 minus P2, x1 minus x2, then we are having a positive upper side and negative lower side. So, if you write the equation, what will be the equation? The equation is Jp, that is given by minus q dp and dp by dx, this is the expression, and we got that this is minus q into dp, and dp by dx will have a negative sign. So, I just write here this is a negative magnitude. If this will give a negative magnitude, overall we are having a positive result here. The value of Jp will have a positive value here. So, what I said, if the value of any current is positive, then we can say that the direction of current is in a positive x direction. So, I think you understand what is the importance of extra putting the negative sign here. Okay. So, if this is a positive result, then definitely we can say that, observe here the holes are moving. Suppose I will take some holes. Okay. So, observe here, suppose this is having so many holes, and the holes concentration on one of the side will be greater than the holes concentration on the other side. So, as we move along the distance, the concentration of holes are decreasing. What is the direction of movement of holes then? The direction of movement of holes in this particular graphical, this is the direction of movement of holes. That means the holes are moving in this direction. So, this is the direction of movement of holes. Then what will be the direction of current? What will be the direction of current? Sir, direction of current is in the same direction, that is positive x direction. So, if you plot a graphical plotting here with respect to distance like this, and this will represent the concentration. So, y axis representing the concentration which is changing with respect to distance, that is x in centimeter, then we have observed that the holes are moving in positive x direction. If the holes are moving in positive x direction, what will be the direction of current? The current is also in the positive x direction, because if the holes are moving in this direction, the electrons are moving opposite to the direction of movement of holes, that is nothing but the bounded electrons. So if the electrons is moving in opposite direction, holes are moving in this positive x direction. So the direction of current is again positive x direction. Okay, so we are having I, okay, this is I diffusion due to holes. So we got the same thing, that is positive x direction. We can see that positive x direction, and this is only possible if you put a extra negative sign in the equation. So I just want to take care that we have to put a extra negative sign on the expression of this current, otherwise we are not getting the similar one that we want in the direct because of the movement of current in direction, either it is positive x direction or negative x direction. Okay, Abdul Khalik Khan, his form has been submitted. Okay, rest of the students kindly submit the form, then we are going to provide some extra material for you. Okay, I am looking into this issue. Okay, this is the message from Ankush. Okay, so he will solve each and every point. Okay, I think you understood what is the importance. So don't think twice. Whenever we are having the current due to the presence of non-uniform electrons, then we have to put with a positive sign. I just put the importance of this positive and negative sign I had given you, and we just have a negative sign here, and don't think twice while putting the positive and negative signs. Whatever will be the movement of the charge carriers, we just put the formulas. Think about these formulas, and I have given you what is the reason we have put a negative sign here and we have put a positive sign in that. So it will represents the direction of current, either it will be a positive x direction or negative x direction. Okay. So this is all about this one, that is the diffusion current, and we just learn the importance of diffusion current. So now come to one more point, that always I am writing within the semiconductor. Why I am not telling outside the semiconductor? So I just put this similar thing in another way. Whenever we are having concentration difference, so I have a quiz for you, and answer that quiz, and then we are going to move further. Okay. If we have, if we have concentration difference, which is also known as concentration gradient, within a semiconductor, then do we have the potential difference within the semiconductor? Answer: either we can say yes, so this is my question that goes to you. Vishwanathan Sarkar, where is the form link? The form link is in the comment box. You can see by scrolling up. Yes, this is the main point we are having. So we are having a potential difference within the semiconductor. So whenever we are thinking about the concentration difference within a semiconductor, due to the change in concentration, there exists another current which is known as drift current also. So this potential difference, if you are taking about yes, then I can write this potential difference, will give rise to another current within the semiconductor and that current is drift current and I would like to write which results overall current in within the semiconductor is 0. So, this is the very important point, you just remember this one. Whenever we are having a concentration difference, there exists a potential difference, and if there exists a potential difference, this potential difference will give rise to another current within the semiconductor, and that current is the drift current, which results the overall current within the semiconductor is 0. So, what is the conclusion of this one? So write down, we don't have any current in a semiconductor in a steady state, that means the final state, steady state condition due to concentration gradient. So, because it will become a 0 current, so we can write we do not have any current in a semiconductor in a steady state condition due to the concentration gradient. We only have the current, we can get the current in a semiconductor if we apply any source externally to the semiconductor. Which semiconductor? We can get the current in a semiconductor if we apply source externally to the semiconductor, if the semiconductor is uniformly or non-uniformly So, either we are having a uniformly doped semiconductor or non-uniformly doped semiconductor, the magnitude of current will be equal to 0 until unless we are not applying any external source. So, if we apply external source only, then we are having a current within the semiconductor. So, I just write here, so this external source, okay, this external source will maintain a constant supply of the charge carriers, constant supply of the charge carriers either by electric field or any other source. So, we have a visualization over this one. Is drift current equals to diffusion current? Then we are having the current equal to 0. That the same thing I have written here. So, within the semiconductor we do not have a current. The reason is that we are having the diffusion current within the semiconductor, and this diffusion current will give rise to a potential difference within the semiconductor. Due to potential difference, we are having another current, that is drift current, which is equal and opposite to the diffusion current. Then we do not have any current within the semiconductor, and the magnitude of current will be equal to 0. Okay. So, if you are not understanding these wordings, then definitely we have to visualize the things in a proper way. How to visualize the things? We are going to draw a simple body, semiconductor body, and this semiconductor body is non-uniformly doping. That is, suppose we are having the concentration here, N1, and here we are having N2. So, N1 is greater than N2, and this is the position x1 and this is x2. Each and every point here is very important, because in GATE they are asking many questions based on this particular concepts. We are having the question based on this concept many times, and we are facing difficulties in solving this question or understanding this question, because sometimes the magnitude of current will become 0, and sometimes they are not taking the magnitude of current equal to 0. Why? What will be the reason? The reason is this much. Okay. If we are in crash course, we have to understand each and every point. So, tomorrow we are going to take some question based on this particular concepts, and while taking the question that is based on this particular concept, we just remember this concept very thoroughly. Okay. So, this is very important for everyone who is appearing for GATE examination, either in 21, 22 or in the previous year they are facing the difficulties solving this particular question, because they have not understood the reason behind this one. So, we are having the concentration difference. So, we have not applied any external electric field. So, if you are not applied any external electric field, there is no current existing. So, we have to think within the semiconductor and outside the semiconductor. Then again we are taking another one in which we are going to apply an external potential. Okay. So, this will give an idea how we are supplying the charge carriers externally. So, we are having an external potential, and by using this is not open circuited one, this is having some external potential applied externally. So, this will supply the electrons within the semiconductor constantly. So, this is positive, negative. In this way we have to think. So, I will give you the idea. Here definitely we are having a current. The magnitude of current must be equal to a non-zero value. So, here we are having the current that must be a non-value 0. So, this is a non-value 0, because we are supplying constantly the source which will supply the electrons, because the negative terminal of the battery will supply the electrons. Okay. So, if you are having the concentration difference here also N1, N2, and at between 2 point x1 and x2, then here the same thing, and we can say the N1 is greater than N2, but the current magnitude is not equal to 0. Here we are having the similar thing, but without applying any external field, then we are having the magnitude of current is equal to 0 within and external to the semiconductor. So, there are two different things that we have to think twice before answering your question. So, what is the potential that has been developed within this? So, if you take 2 points within the semiconductor having the potential V1 and V2, then because of the movement of charge carriers, just now we have seen that here we are having positive sign, because the electrons concentration is greater. That means this positive sign represent that we are having donor atoms on this side will be greater, and this is some positive with electrons. What are these all things? These are known as the donor atoms. What are they are? They are nothing but the donor atoms. Okay, they are nothing but the donor atoms. And here we are having again donor atoms, but the concentration of donor atoms will be less. So, here we are having like this. So, what will happen? Due to concentration difference, the electrons from this side has been moved to the other side. This is the direction of movement of electrons. So, if the electrons has moved from this side to this side, then what will happen? The concentration of electrons will be greater on this side, and because the electrons goes from this side, this will have less electrons. So, 3 electrons move to this side, and this side will be lost of 3 electrons. So, what will be the charge on this side? On this side we are having the positive charge, because these two are neutrals and we are having positive, 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 that means 3 positive charge. These two are neutrals, we are having negative, 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 that means we are having negative sign here. So, electrons are moving in this direction. What is the direction of movement of electrons? This is the direction of movement of electrons. So, what is the direction of movement of diffusion? What is the direction of diffusion current? So, diffusion current always flows in the opposite direction to the direction of movement of electrons. So, in this semiconductor, this is the direction of diffusion current. So, this is the direction of diffusion current. Okay. Now, what will happen? Because of the movement of electrons, there exists a positive potential here and negative potential here. Always we know that if we are having a potential difference, definitely we are having an electric field. And what is the direction of electric field? The direction of electric field is in this direction. So, this is the direction of electric field within the semiconductor. I just write this is the electric field direction. If we are having electric field within the semiconductor, because of the presence of ions, donor atoms, that will become ions now. So, this particular point I will represent that this is the ions which is present after the movement of the electrons on the other side. Then what will happen? We are having the electric field in this direction. In the presence of electric field, again the charge carrier is moving and we are having a drift current opposite to the direction of movement of the diffusion. So, we are having the drift in the opposite direction. So, we are having the drift in the opposite direction. So, inside a semiconductor, the overall current has been measured by addition of diffusion and drift current. So, if we add the net current within the semiconductor, that is I net, this is equal to the addition of the diffusion and the drift current. So, plus the I drift current, and we have seen that diffusion and drift are opposite to each other. So, overall current within the semiconductor will become 0. This is one gate questions. This is one gate question. And again we are having another one. The similar concept has been applied. Here we are having potential, that is V1 and V2. Here we are having positive, negative. That means the overall current within the semiconductor will become 0 because of the addition of diffusion and drift current, which is equal in magnitude and opposite in direction. So, this is in opposite direction to each other. So, we are having a negative sign here, that why we are having a current magnitude is equal to 0. Now, in this particular semiconductor, there exists a current which is diffusion current, there exists a drift current which is opposite to this, and within the semiconductor there is no current. So, current magnitude will become 0, but because of the addition of external electric field, the drift current will be dominated, or we can say the diffusion current. Okay, the diffusion current will be dominated by the overall drift current because of the presence of another electric field outside the semiconductor. Now, what will happen? Here we are having the overall current has been measured by adding this particular drift current, which is additional current present within and external to the semiconductor, and this drift current can be measured by using the electric field externally which is present outside the semiconductor. So, we can write this is NQ mu n into electric field into area of cross section. This is the additional current, and here the magnitude of current will not be equal to 0. So, if you are having a constant supply of charge carriers from outside the semiconductor, instead or in addition of the presence of diffusion within the semiconductor, then definitely the magnitude of current will not be equal to 0. So, this is the concept I want to tell you, and we can measure what is the potential that is present. The potential can be measured by using the equation. This is known as contact potential, this is known as contact potential, and this contact potential can be written in this order. This is given by V1 minus V2, and this V1 minus V2 can be written as this is KT upon Q into ln, and this is given by the concentration difference N1 divided by N2. So, if you do not have a concentration difference N1 and N2, we are having the potential that is equal to 0, and V1 and V2 are the potential points between these two concentration difference. So, whenever we are having concentration difference, we just maintain the same thing, that we are having a potential difference, and because of this one the overall current within the semiconductor will become 0. That is why we are not feeling shock when we are not applying any external electric field to this semiconductor. Instead, or if you are having the concentration difference, that too we are not having any shock because of the presence of the drift current, which will counter attack the diffusion current, and overall the current magnitude will be equal to 0. We can measure what is the potential difference exists between these 2 points, and this potential difference always taken the ratio of N1 and N2. So, if N1 is equal to N2, that means the concentration between these 2 points will be equal, the potential difference will become 0, because ln of 1 will become equal to 0. So, whenever we are having the concentration difference, we are having a potential difference, then but all these things are taking place within the semiconductor. All these things are taking place within the semiconductor. That is why I have written within the semiconductor. Okay. So, I have written within the semiconductor. But external to the semiconductor, we are having a current if we are having an external electric field. If we do not have any external electric field, we do not have any current outside the semiconductor or within the semiconductor. If you are getting a current outside the semiconductor, definitely we are having a current within the semiconductor also. So, by this one we can say that there exists a current in this particular direction. So, this is the direction of current because of the presence of the electric field, and this is the direction of current. It is existing within the semiconductor, external to the semiconductor, and this current is due to the presence of external electric field. That is why it is not equal to 0. So, very important each and every point. If you have taken care properly, then only you can be able to understand the questions that is asked in previous year GATE, otherwise you cannot. So, I want to thanks each and everyone, those who are attending the classes. I am finishing my classes today in 1 hour, and in this 1 hour I think I have given you so many concepts and I have cleared your doubts, and while solving the question numerical problems, we are going to visualize the things that we have written today. So, I will meet you again. I am signing up now, and I will meet you again tomorrow morning at 11 a.m. Till then, you just take care of yourself, enjoy the festival, and take care, and I want to say goodbye.